session of this morning of the third day of the conference. And the first speaker would be Marco Pingaro, who is going to talk about fast homogenization procedure for particle composite material using virtual element methods. So, okay, please, Marco, I believe you can.
Okay, thank you so much for the introduction. First of all, I would like to thank all the organizer of the workshop that give me this opportunity. My talk focuses on the homogenization of random composite material using virtual element. Before starting the presentation, I would like to spend 1 minute to introduce myself and the research group. I am a postdoc researcher at Sapienza University under the supervision of the Professor Tavalusci, that she is the leader of the research group. The research team is composed by several postdoc researchers and PhD student of Sapienza University and other university, and they are here reported. So this is the outline of the presentation that it's divided in 5 principal sections. First of all, some general motivation of the work will be given, and after that I will introduce the homogenization technique, focusing on the statistical homogenization adopted in this work and the relative automatization using the virtual method. Furthermore, some numerical tests will be presented, in particular for porous material, and the first results obtained for polycrystalline material with thin interfaces. And finally, some remarks and future development will be illustrated. So, a large range of material used in different engineering applications exhibit a random structure with random inclusion dispersed in a matrix. They include classical materials such as concrete, porous rock, and masonry, or advanced material like metallic form and ceramic metal matrix composites. Study this type of material is an open challenge for their complex behavior. In this context, homogenization are successfully adopted by several authors for classical and enriched continuum, and the synthetic literature, non-exhaustive, is here reported. But what is the object of the homogenization? The object of homogenization are the estimation of the elastic, homogenized elastic moduli, and the determination of the representative volume element that do not a priori define in the case of random material, in which is not possible to identify a repetitive cell. Regarding the model, we consider a 2D model in which the material is modeled as a B-material system, and all components are considered linear elastic at this stage. Currently, 2 idealizations are taken into account. The first one is disc shape inclusion of diameter d dispersed in a matrix. And the second one is polygonal inclusion with thin interfaces. Regarding the first assumption, the deterministic parameters are the average density of the medium, the dimension and the shape of the inclusion, in this case, circular inclusion, the mechanical parameter, and the minimum distance between the inclusion, that in general in literature is called the R-core distance. The random parameters are the number of the inclusion and the position of the inclusion. I underline that it's very important to consider the crossing of the inclusion on the window edges, because it was being shown that not taking this into account invalidates the results that will be archived. For the second model, the deterministic parameter are the mean dimension of the grains, the mechanical parameters, and the thickness of the interfaces. And the random parameter are the number of the inclusion, the position of the inclusion, and the relative shape. As mentioned, in the case of random material, a statistical procedure is necessary. It's possible to summarize the procedure in principle 6 steps. The first step, in the first step, we set the nominal volume fraction of the medium, the diameter of the inclusion, and the core distance between the inclusion. We choose a trial dimension of the window size, and after that, it's possible to define delta, that is the normalized window dimension. It's defined by the ratio between the window dimension and the radius or the diameter of the inclusions. At the second step, we define the expected number of inclusion using a Poisson distribution. At step 3, for all realization, we randomly generate the position of the inclusion. And this strategy corresponds to the so-called moving window technique. After that, in step 4, we apply over all cells Newman and Dirichlet boundary conditions, and we solve all boundary value problems. And after that, it's possible to compute the relative homogenized constitutive parameters. After that, in step 5, we repeat the step 2 to 4 by increasing the window size. The procedure stops when we reach the convergence, and typically we obtain similar results sketched in this figure, where the Dirichlet and Newman boundary value problems define the upper bound and the lower bound of the solution, respectively. The statistical criterion adopted for stop the procedure allows to stop the procedure when the number of simulations necessary to obtain the average elastic coefficient that do not differ of a given tolerance, and that's depending on the data dispersion of the results. I want to notice that the adopted converge criterion is valid for any value of the material contrast, and the material contrast is defined as the ratio between the Young modulus of the inclusions and the Young modulus of the matrix, and will be used for the define different type of material, for classify different type of material. The procedure illustrated have an high computational cost. The main problem is that do not permit to perform a series of parametric analysis. For this reason, the procedure has been automatized in a code totally in-house implemented, the so-called fast statistical homogenization procedure, FSHP. And by using FSHP, it's possible to obtain fastly the convergence of the procedure, more or less in a couple of hours. Recently, the procedure has been improved to take into account polycrystalline inclusion with thin interfaces. In this case, we adopt Polymesher, developed by Professor Paolino, as a tool for meshing the geometry. The idea is to generate an initial Voronoi tessellation, random Voronoi tessellation, and using Polymesher. And after a shifting procedure, the interfaces between the grains can be created. In the performance analysis, we adopt the VAM elements, and whose characteristics are well known in this Congress. But I just want to highlight the ones that I will be using. Certainly, the first one is the possibility to have a polygonal element of any shape. Furthermore, the capability to easily use the hanging nodes, and the possibility to coupling FEM with VAM. These features are used for creating a specific ad hoc mesh for the analysis performed. In particular, for both type of mesh, we adopt a singular element for the inclusion of for the grains and a triangular element for the matrix part. In the case of circular inclusions, in case of singular inclusion, the mesh is fine near the inclusions and coarse elsewhere. For reducing the time consuming. Time consuming in the case of particle inclusion is here reported. The graph shown the time analysis in seconds at vary the window dimension. In blue line, the time consuming of the standard FEM of degree 1. And in red line, the time consuming of the VAM of degree K1 adopted in this strategy. The maximum reduction of the computational time is more or less 25%, and apparently is a low value. But when we perform 100 of an analysis, the reduction for the procedure in time is very consistent. While in the case of polycrystalline material, the reduction in terms of degrees of freedom is about 300%. Is a very high value. Now I want to show some results obtained by the procedure by FSHP. The first numerical result is a comparison between the previous procedure that used FEM of degree k equal 2 and the new procedure with VAM of k equal 1. We consider two types of materials, one with stiff inclusion and one with soft inclusion. The mechanical parameters are reported in this table. The two graphs shown the homogenized bulk modulus versus the normalized window dimension. In red line, in red and blue, the results obtained for Dirichlet and Newman boundary condition respectively. The circle marker is adopted for the old procedure and the cross marker for the new procedure. What can you see in this graph? You can see that in the case of soft inclusion, the solution obtained with FSHP procedure is in very good agreement with the previous one, but in the case of stiff inclusions, the result of the new procedure don't match the results of the old procedure. And this is strictly related to the high gradient of stress around the inclusions. Another interesting result is the possibility to model large window. And this is, of course, related to the reduced number of degrees of freedom using the VAMS methodology. This is very important because, especially for the material with very high or very low value of contrast, which request a high window dimension for reaching the convergence of the procedure. For the reason described, we focus the attention on the porous media, and we consider a material with a very low contrast. The adopted mechanical parameters are reported in the table. And first, we study the case of high average density, that in this case is the porosity of the material. In this slide is reported the minimum number of simulation here. It's reported the minimum number of simulation and required for reaching the convergence at vary the window dimension. In red line, the directly boundary condition, and blue line, the Newman boundary condition. The two bounds tend to decrease, and they tend to the same value when the window dimension is decreased. Is good. Then here is reported the value of the normalized bulk modulus. At the window dimension is increases, the two bounds tends to get closer, even if there is a mismatch between the two bounds, because the two bounds became more or less parallel. These differences in terms of convergence strength depend on the different data dispersion of the results. In the two left graphs shown the normalized average bulk modulus, in red line, in red the Dirichlet boundary condition, and in blue the Newman boundary conditions versus the number of simulations for different window dimension. And in the right part of the slide is reported the coefficient of variation relative to the bulk modulus at vary the window dimension. After that, we study the sensitivity to the porosity. We analyze a different level of porosity, starting from 5% to 40%. As intuitable, the homogenized moduli decrease when the porosity increases, such as the bulk modulus here reported. While for the homogenized Poisson coefficient has a particular behavior. It decreases at increasing the porosity. That is normal. But the two bounds are exchanged in the sense that the Newman boundary condition is the upper bound of the solution, and the Dirichlet boundary conditions is the lower bound of the solution. And concerning the dimension of the representative volume element respect to the porosity is linear increase in the range of 5 to 20%, after that decrease, and after more or less 25% became constant. Now I switch to the polycrystallar. So I want to present some initial results obtained applying the statistical homogenization to polycrystalline material with thin interfaces. The first result is a comparison between the proposed procedure using FEM and the standard procedure with FEM. FEM assuming as a reference solution. In the two tables are reported the homogenized elastic moduli for a different level of contrast. In the case of the Euclid boundary condition and in the case of Newman boundary condition. As you can see in this result, the results are very good, and the maximum error is less than 1%, with an high reduction of computational cost. In the upper part of the slide, I reported the number of nodes used for the two different meshes. After that, we started to study, we consider for constant contrast of material, 2 for stiff and 2 for soft grains, respectively. And this slide is reported the bulk modulus to vary the window dimension for soft inclusions and the relative coefficient of variation Same results, it's possible to obtain the same results for the stiff inclusion. More or less the trend is the same. As you can see in these two examples, the homogenized bulk modulus remains constant, increasing more or less in constant, increasing the window dimension. But the coefficient of variation give a convergence trend for the represented volume element. So in order to conclude this presentation, some final remarks are here summarizing. The main goals achieved are the total integration of the statistical procedure using the VEM methodology, in particular adopting the VEM of degree k equal to 1 that permits a reduction of the computational burden. The adoption of VEM permits a large scale campaign of analysis for different type of materials, such as material with circular or polygonal inclusions. Further development are manifold, starting from the use of enriched continuum to improve the description at the meso and micro and meso scale, to use a high order VEM to solve the problem related to the rigid inclusions. Furthermore, study the influence of the shape of the inclusions, such as the fiber dispersed in the matrix part of the material, or material with 3 or 4 physical components with the different percentage of volume fraction. And that's all. And thank you so much for the attention. And
thank you. Okay, thanks Marco for interesting talk.